Good afternoon, everybody. Welcome back to the keynote session of the 8th International Conference on Biosignals, Images and Instrumentation for the year 2022. To stimulate our inventive instincts, we have with us the first speaker of the afternoon session, Dr. Rahman S. Malik Sharif. He is the project leader of biomodels at the European Bioinformatics Institute, European Molecular Biology Laboratory, Wellcome Trust Genome Campus, United Kingdom. He is an experienced scientist with a demonstrated history of working in research industry. He is skilled in mathematical modeling, multivariate statistics, bioinformatics, digital image processing, and big data analytics. He also leads a team of members to develop novel approaches, tools, and resources for modeling biomedical systems. With a PhD, he focuses on finding patterns in big and complex biological data set and modeling quantitative causal network from Max Planck Institute of Molecular Physiology and TU. We welcome you, sir. The session is all yours.
Okay, can everyone see my screen and hear me well?
Yes, sir. We're able to see the screen.
Thank you. I'm sorry for the delay. I had some network issues. So I'm going to keep my video off so that at least you hear me well and see my screen well. Right, so good afternoon. So thanks for the kind introduction. So in this talk, I'm going to discuss with you how we can use imaging, more specifically quantitative imaging, to understand the dynamics of cell signaling networks. Okay, sorry. Right. So see, we all know a living cell is a remarkable system. It's highly dynamic. It responds actively to extracellular signals, responses to the extracellular environmental changes and so on, so that it can perform its function actively. So it can get any, if there is any signal, let it be a growth factor or any chemical perturbation, the cell responds to that with changes either in the gene expression, it can be segregation of a protein or changes in the cytoskeleton, or it can be growth of the cell if it's a growth factor. All these changes the cell execute are decided through this information processing unit in the cell, which is the cell signaling network. So this network is acting as a CPU of the cell. So it computes the signal and decides what is the output of the signal. So it connects the input of a cell to the output, the cell signaling network, establish this connection. The cell signaling network also helps to tune the response, which means for any given input, you can have a desired output, or you can know what is the strength of the output. And also it determines the dynamics of the response, which means it tells how long a cell has to decide, has to generate or synthesize a protein and express it and so on and so forth. So a cell is highly dynamic. It has all these functions, and these functions are controlled by the cell signaling network. So today we're going to talk about understanding these cell signaling network or protein networks in cell matrix addition sites, which is a very good system to study how different proteins come together, connect to each other, and that connection, complex network, is responsible to execute various cellular functions. So cell matrix addition sites are macromolecular structures that help attachment of the cells along the plasma membrane. And they have various functions. The primary functions include addition of the cell, sensing the environment, modulating the extracellular matrix. Besides that, they have several more functions that help in the cell attachment, help in the migration of the cell, for example, during embryonic development and morphogenesis, and help in wound healing. Whenever there's a wound, you see the cells migrate from the periphery to the center, and they heal the wound. This is controlled and helped through cell matrix addition sites. And also these addition sites can transmit signal, and they can also control fate of the cell. Some of the interesting feature of these addition sites are that they are multi-component structures. They are made of more than 150 different proteins, which means they are highly diverse in their molecular composition. Addition sites could be made of different networks, and of course, different networks will have different connections and different composition. Right. So, additionally, these structures are also highly dynamic, which means they're rapidly formed in the cell and also rapidly destroyed in the cell, as you can see in the movie in the right. So they are formed in the front edge rapidly, and then also removed from the rear edge. This is a dynamic process, and it happens very, very quickly. So I was trying to understand the structure and functional relationship of these protein networks in addition sites, and I tried to adapt an imaging-based approach, where, of course, you need an imaging because these protein networks are made of several proteins, and we need to explore them one by one at a time, or simultaneously as much as we can together, to understand how they are formed and how they function. What are the structure of these protein networks? So in a same cell, the hypothesis that there are different conditions. Due to different conditions, the cells can build different protein networks which will have different composition and function. So the front, for example, front side of a cell can have different addition site with different protein networks, where you have these proteins connected in different configuration or in different composition, and the rear end can be different, and they can have different role in helping migration of the cell. Okay, so essentially what we're trying to do is trying to understand what are the different structures, what are different proteins, and how cells take those proteins, put them together to form different structures. And of course, there is a network organization in these structures, and try to understand that. Right, as I said, we have to follow an imaging approach because we wanted to image many proteins, follow multiple proteins. So we try to image all these proteins in these cells. How do we do that? There are fluorescent proteins which can be tagged with our protein of interest and generate a hybrid protein. So these will help us to track or follow all our protein of interest and see where they localize, quantify them, and use this information to understand the structure and the function of these proteins. And we look at multiple proteins simultaneously, we can try to infer the structure and behavior of the protein network. Okay, so here's an example. So you can see you have this GFP tagged to tubulin, and you can see the organization of these structure in the entire cell. And you can see the red M-cherry tagged to mitochondrial region. Protein that localizes in mitochondria. So you can basically tag a protein of your interest, which means you clone your gene of interest with the genes, the fluorescent protein, and you can use this to ectopically express, use this vector ectopically expresses hybrid protein in the cell. And when the cells expresses hybrid proteins, these proteins will localize where they are supposed to, where they are, and then it goes everywhere and does a function. But by imaging, you can follow where does the cell localize and what kind of function does this protein, where does this protein localize and what kind of function does this protein do. That's the basic idea. But in our case, we wanted to image multiple proteins, which is not easy. So what I did was trying to understand 4 different proteins in cinematic addition sites. These are the proteins are zixin, vinculin, fucosyl kinase, and paxillin. These proteins have different roles in addition sites. Zixin is in the actin regulatory layer. This is the layer that connects the addition sites with the the actin filament in the cell. And this is very important because the actin needs to pull the adhesion site. And this pulling is very crucial to keep them intact. If we inhibit the actin filament by adding this ROCK inhibitor, which is going to disrupt the actin filament, then the adhesion site will also disassemble. So what we can do is we can actively add this inhibitor, which inhibits the actin filament, and thereby takes away the force. The adhesion sites will be forced to disassemble. So we can then wash this drug out, and then these adhesion sites will form again. We can repeat this cycle and try to understand how the adhesion sites respond to inhibition of force and how they are disassembled and assembled, and what kind of protein networks are responsible for building adhesion sites, and what kind of protein networks are responsible for disassembly of the adhesion sites. So here, to image these proteins, I developed a 4-color imaging system where simultaneously 4 different proteins of our interest are tagged with fluorescent proteins and imaged simultaneously. So I have taken all these 4 proteins, zixin, vinculin, focalization kinase, paxillin, and tagged them with 4 different fluorophores. Of course, sometimes I have to use two fluorophores to increase the signal. This is a part of optimization we need to do. And these fluorescent proteins can be now simultaneously imaged in the same cell, in the same structure, without spectral breakthrough. So this approach, I could express all these 4 constructs in the single cell and find cells which have all these 4 proteins expressed, and we can now image these 4 proteins simultaneously. As you can see, these are the 4 proteins nicely localized in their localization, in the focalization, and doing their function. Okay, so now it's not just imaging as a snapshot, we also do a time course imaging. So we did a time-lapse imaging where we follow single cell and follow adhesion sites over a course of time, and also, of course, we subject them to the inhibition of force, which leads to disassembly and assembly of the adhesion sites. So we follow them, we have nice images, but now to understand these protein networks, we have to quantitatively analyze them. Before quantitatively analyzing them, we have to process these images. For that, I developed lots of quantitative image processing tools. So which includes correction for any chromatic aberration. Chromatic aberration is the natural phenomena that occurs when light gets deviated from their path. So we have to put them together so that all the small structures focus on the same region. I mean, forms in the images we have, we cannot do that. So we try to use correctors through lens, but we also try to correct this computationally by finding the aberration by imaging beads and correcting the image according to that distortion. And then we have to also do background and bleaching correction. There could be bleaching in the images which has to be fixed, and we should also perform low pass and high pass filtration, and also do some lateral shift correction. Okay, at the end, our objective is to understand how different proteins in the cells are put together by the cell in order to build different types of protein networks or protein machineries, and how they are used to perform different cellular function. Right. So to do this, we have imaging. Now I need to understand the protein networks and the adhesion sites. So for this, I use an approach called compositional imaging. So this is a computational approach developed to first identify and then also visualize protein networks and their dynamics. So let me show you an example in a simple three-color imaging data, so that it's easy to discuss about this method. Right. So let's say I'm imaging adhesion sites, and then I'm looking at only 3 proteins. So I have 3 different fluorescent tags. So which means I have 3 images in all the 3 for each of these proteins, representing different fluorescent tag. So what I can do is each image, as you know, is a collection of pixels, and I can take these images, collect the pixel from each of these images, from every single addition sites and every spatial structures, and place that pixel in a three-dimensional space. And this space I call as compositional space. So in this space, the dimension corresponds to the level of this protein. It can be the activity of the protein and so on. So in my case, it's the level of the three proteins I'm looking at. You can collect all the pixels, not just one pixel, all the pixel from all the images from all the time points, so that I will have a cloud of pixel in this space, in a three-dimensional space. And the location of each pixel is determined by the X, Y, Z coordinates, which are basically the level of the three proteins here, which I'm interested in. So you can expand this approach. If you have 4 images, you will have to place them in a 4-dimensional space. Right, so now I'm going to cluster these pixels and try to identify compositions or protein networks which have similar compositions. So this I achieved through hierarchical clustering. It's nothing but grouping the pixels together so that similar pixel with similar composition are grouped together, and we give them a tag. So through this approach, then I could identify there are 3 compositions or 3 clusters in the network, or it can be called as 3 different protein machineries or protein networks. A, B, C, D, I label them. This is just because it's an example. And of course, they have different composition. And then what I can also do is that I can map them back into the images, because I know where these pixels came from. Because although these pixels come from different images, they're coming from the same location in all these images, right? Each pixel is having the same location. So I can map them back and then identify the signatures, the compositional signatures localization, how they're organized, and we can follow their function. For example, if I treat these cells with a drug that lets the assembly of the addition sites, you can follow the movie and see what are the additions composition or protein networks which are formed during the assembly of the addition sites. Okay, let's go back to a small schematics. So here we have proteins A, B, C. We try to collect all the pixels from the images, place them in this three-dimensional space, and try to understand the protein network by clustering them, which means we group those pixels which are having similar composition, and they have similar composition because they have different protein network states. Now we can map these back into the cell and ask where these different protein networks or network states are localized. So now let's go back to the real example here, a real experiment where I made 4 proteins, zixine, alpha-actin, vinculin, and paxillin, and identified about 8 different protein network states. I mean, you can have any combination. When you have 4 proteins, you can have endless combination of these proteins, but in reality, cells form only these 8 different protein network states of composition. So the compositional imaging approach can help us identify this, and we can spatially map these composition of the networks, understand how they are spatially organized, and you can see several beautiful images of the cell. They have different spatial organization. Of course, as these are movies, we can also follow every single cell and see what are the function of this different composition, how they change over time, how they are spatially organized, and so on. So on the left-hand side bottom, you can see that the compositions are equally abundant in all the fibroblast cells, and they are pretty much comparable across these cells. I mean, you can also, instead of looking at the entire cell, what I also did is look at single focal addition sites, just remove everything. So addition, this protein can also localize outside the cell, so we kind of ignore that and just look purely into the addition sites. And nicely, we can see very good organization of the protein networks or protein machineries. You can see these inside these addition sites. They have different patterns. So here in this case, I have identified about 6 different compositions of protein network states, and the red one, which is rich in alpha-actinin, here is towards always the center of the cell, and The orange one, which is rich in paxillin, just away from the center of the cell or towards the periphery of the cell. So you have clear organization of protein networks within the cell matrix addition sites. Of course, you can also follow addition sites when they're assembling or disassembling or remaining static, and try to see what are the functions. So if you see here, addition sites on the right hand side, which are not having these alpha-actin tail, do not disassemble, whereas those which have those tails start to, do not migrate, but those which has this active tail with E composition, which is rich in alpha-actinin, tends to also slide down during migration. Okay, so now let's discuss about this important experiment where we look at the mechanical perturbation, which I mentioned earlier. So we looked at these cells, perturb them with actomyosin contractility inhibition twice, and see how these cells respond and identify different composition. And we can follow every addition sites and analyze them and find compositions that are upregulated and downregulated in these inhibitions. So there are more interesting results, but I'm going to let you read that manuscript and learn more. But the essence of this is that we can identify how different compositions are formed and how different, which means different protein networks are formed and how they change over time and how they respond to different mechanical perturbations. So here, this approach helps you to identify how different networks are formed. I mean, what are the networks that are formed? We do not know how these networks are formed. Of course, we know to the extent that these are formed when you inhibit a mechanical force or if you restore the mechanical force in the cell, but we do not know how they are formed. I mean, how different proteins come together and form. So for this, to identify this, what I did is I tracked every single addition sites, quantify the level of all the proteins, and try to identify how different proteins enter or leave addition sites. So basically, it's quantification of every single addition sites, imaging them, segmenting each addition sites, quantifying them, so that you know how different additions are. I mean, follow how different proteins enter, and we can use this to find out which protein enters the addition sites first and which brings other proteins for following that in the addition sites. So again, these are the details which you can learn, but I think using this imaging and quantitative analysis, at the end we learned a lot from the mechanoresponsiveness of the focalization sites. We understood that it can fetch or read multiple cues. The addition sites can read multiple cues from the environment, and it can assemble these addition sites together depending on the need to build different compositions to perform various functions or tasks. And of course, I'm not going to go into further details. The main essence, what you need to take is a quantitative imaging. It's an approach that is quite useful to understand protein networks in addition sites for single cells. Another good example I want to show you today very, very quickly. I think in the interest of time, I don't want to go into too deep, but I also want to give you a flavor. So we can also use this to study the protein networks. I mean, of course, these addition sites are structures, physical structures formed along the plasma membrane, but sometimes it could be just a signaling network. The protein network can just be a signaling network in the cell, which means there are proteins which are activated in the cell, and then they talk to each other differently. And through this signaling topology, they can have different cellular function. I use this to study the protein network during differentiation of embryonic stem cells. So embryonic stem cells are pluripotent cells. We know that they can be derived into any adult tissue types. So we took the human embryonic stem cells and we differentiate them in the lab with different growth factors, and we can study how the protein networks or cell signaling network in ESL adapt to become a somatic cell. So specifically, I chose a BMB4, which is a growth factor, which differentiates ES cells into cardiomyocytes or trophoblast-like cells. And again, we try to image these cells, every single cells, along the differentiation, and we can ask when does the ES cell become a somatic cell, and what kind of changes in the cell signaling network, protein network happens during this transition, and so on. So this requires, of course, tracking of single cells. So I wrote algorithms that can identify single cells, track them, follow the division, connect the lineages, and we can use this to ask several interesting questions. So here what you see is CDTA protein that is usually accumulating in the cell during the G1 phase, and when the cell enters from G1 to S phase, this is degraded. You can see nicely on the image, and we can also track lineages, the parent cells and the daughter cells and granddaughter cells and so on, so we can understand how the cell signaling network evolves. We can also use this to understand the decision of the cell. So when a cell divides into two daughter cells, of course, you have two cells which are equally distributed with the content from the mother cell, yet these two cells can have different cell fate. So one cell can either decide to divide first, another cell can divide, but later, as you see, two cells enter into G1 S phase at different time, or one cell can decide to divide, another cell decide not to divide at all. So we can understand how the cell's decision is decided, made by the cell. By following single cells, of course, we can look at the cell signaling network of these individual cells and understand the signaling better. So here, my approach had multiple steps. This involved either using fixed cells, or you can also use image cells, segmenting them, looking at the single cell quantification, and trying to understand various properties of the cell signaling network. So one of the important measurements I did was looking at the level of signaling protein that's essential for maintaining the pluripotency. For example, here you look at the level of UP4, and you can follow every single cell and quantify them and find out when does these cells start losing. And interestingly, what you can see here is that when the ES cells differentiate, the differentiation happens in the periphery, and then it propagates to the center. So you can see on 24 hours after BMP4 treatment, the cells differentiate, they become blue in the periphery region. And then this propagates slowly inside, and then in 72 hours, all the addition sites, all the stem cells, are fully differentiated, and then they become blue in color, which means here low level of OP4. And also, I use imaging sometimes to understand how imaging of the biosensors to understand the activity of the protein. Sometimes it's not just expression; it's also activity. So the CDK1 sensor, which we use, is a protein. It's a peptide that localizes in the cytoplasm in the G1 SGTM phase. But when the cells enter M phase, this enters into the nucleus. So this is because when CDK1 is active, the sensor enters into the nucleus. The protein enters into the nucleus. So we can use this basically to follow the activity of these cells, of the protein in the cell, and find out which cell cycle phase these proteins are highly active. So we can also use other biosensors that are available. For example, CT1 is a good biosensor for G1S phase, and PCNA is another sensor to identify the cells in the S phase and GTM phase, and H2B is another biosensor which we can also use. So by having a series of biosensor, we can understand every protein networks in every single cell. But one last important message I want to also shows that these set of quantitative imaging are also very helpful to understand the networks in a specific biological process. For example, here I used mathematical modeling on top. So the imaging the quantity imaging data can also provide information that can be mathematically modeled to understand the system better. So one thing which I also found very interesting, or is the group found interesting where I worked, was that irrespective of the cell types, either it is embryonic stem cell or red alert cell, the mitosis duration is always constant, about 45 minutes plus or minus 10 minutes, is always constant in all the cell type, either it's differentiated cell or or embryonic cell or any tissue and cells from any tissue type, that the time the cell spends in mitosis is very precise and constant. I mean, of course, the entire cell cycle can be different. Some cells can, I mean, embryonic cells in a really early embryo can take 6 hours to divide and then do the cycling every 6 hours, whereas in an adult cell, differentiated cell, they take much longer time. Adult cells about 20 hours to do the cell cycle. But irrespective of the length of the cell cycle, the cells always spend roughly the same time in mitosis, and we want to understand this. So we to understand this network controlling the mitosis, we did a mathematical modeling. Of course, we use the data from the imaging, quantity imaging. So in this mathematical modeling approach, we try to build the molecular interaction network that we think is controlling the mitosis, and define mathematical equation to establish or write down these connections in the network, and run simulation that reproduces the dynamics of the cells. So of course, you see we can reproduce initially the division cycles of the cell. Now we try to ask what is keeping mitosis constant. Of course, we can do several in silico experiments. We can do all this perturbation in our mathematical model and try to understand, fit with the data, quantity imaging data, and see if we can figure out the reason. Right. So what we found out from this is that, I mean, this is not very critical for this discussion, but what we found out is that the positive feedback loop in the mitosis, in this network that controls mitosis, is very crucial. And if we perturb that positive feedback loop, then the mitosis duration is no more constant. We did single cell simulation, and we also did experiment, and we proved that indeed that's the case. If we perturb V1, which is in this positive feedback loop, it is that which is basically double negative, and then of course it is a positive feedback loop. It is resulting in in a mitotic increase in the mitotic duration, whereas this is not the case in perturbation of MAT2, which is not in the feedback loop of this network. But the essence you need to take is that imaging-based data is very crucial also for such modeling approaches. So I will let you read this manuscript a bit more to learn on how I did modeling and how we use this imaging data to understand why mitosis is always precise and constant in multiple cells. And of course, as I told, mathematical modeling is getting very important. I would also welcome you to read this manuscript where we provide free mathematical models. So it's not about imaging, but of course it's a different topic. But this is something which I'm currently working on. I'm interested in mostly using mathematical models to understand the cell signaling network. So you can read the manuscript more to get more insight. So okay, with this, I finish my presentation. Thank you for listening, and I'm happy to take any questions you have.
Thank you, sir, for the detailed presentation on computational analysis, compositional analysis, and computational imaging for visualizing protein network states with clear illustration. Thank you for providing us a flavor of cell expression, cell signaling, and quantification of cells. Thank you, sir, for being with us today. We are happy to have you.
Yes, my pleasure to join you. Yep.
Thank you very much, Dr. Rahman Sharif, for sharing your thoughts and for the nice presentation. We thank you once again for accepting our invitation. Thank you very much, Dr. Rahman Sharif. Thank you.
Oh, thank you. Apologies for the delay due to the technical issue, but I hope you could hear me well.
Yes, no issues, Dr. Rahman. It was all fine. Thank you very much.
Thank you.
Over to Tuhina.
Good afternoon. We would like to inform you that there is a slight delay and a slight change in today's schedule for the keynote session. Our next keynote session will be at 2:30 p.m. since Dr. Sean Joseph Smith is unable to join us today as per schedule due to personal commitments. Hence, our following keynote speaker will be Dr. Renu John, Department of Biomedical Engineering, IIT Hyderabad. Kindly join us at 2:30 p.m. for the next session with Dr. Renu John. You could stay on the same link until the doctor joins us. Welcome to the final keynote session for the day. I would like to introduce our next speaker, Dr. Renu John. Dr. Renu John is a professor in the Department of Biomedical Engineering at IIT Hyderabad. He obtained a PhD in physics, optics from Indian Institute of Technology, Delhi in 2006. He served as a research associate at the Fitzpatrick's Center for Photonics, Duke University, Durham, USA, from June 2006 to May 2008, and at Beckman Institute for Advanced Sciences and Technology, University of Illinois, Urbana-Champaign, USA, from May 2008 to November 2010. His journey with the Department of Biomedical Engineering at IIT Hyderabad began in 2010 from assistant professor to professor and head of the department. He is the co-founder and head of Center for Healthcare Entrepreneurship, CFHE, at IIT Hyderabad. It was established in 2016 with an objective to catalyze healthcare innovation with a focus on affordable solutions to address healthcare needs of India. His areas of expertise include biomedical imaging, optical coherence imaging and microscopy, nanoparticles, and target-specific imaging. We are pleased to have you with us, sir. I'll leave it to you now to continue with the session.
Good afternoon to all of you.
Good afternoon, sir.
Hi.
Hi, sir.
Give me a minute. I'm just sharing my screen. Am I visible
Yes, sir.
and audible too, right?
Yes, Professor. Yes.
All right. So can I start?
Yes, please, sir.
So good afternoon to all of you. It's my pleasure to be with you for this session. And I thank the organizers for inviting me for this session. So in this session, what I'll just have a quick overview about optical coherence tomography and a couple of clinical applications that we have been trying to develop, or we have been currently carrying out with the hospitals. So broadly speaking, when we comes to biomedical imaging, we are looking at different types, like we call them as non-invasive or invasive imaging, or minimally invasive imaging, and then we also look at ex vivo imaging, and then even in non-invasive imaging, there is something called in situ, when the tissue is not taken out from the body but is imaged on the site itself. So there's a broad class of imaging modalities in clinics, starting with the common ultrasound to X-rays and CTs. Then a class of instruments which uses the radio tracers or radioactive elements for imaging, like positron emission tomography and SPECT, and MRI, which is probably the least harmful or totally harmless imaging without radiation. And on the other side, there are a class of imaging technologies which are primarily looking at light or photons for imaging. So we broadly call them as photonic imaging, photonic or optical imaging technologies, which includes like the regular fluorescence or luminescence, then a class of imaging modalities like Raman spectroscopy or Raman imaging, coherence tomography, and there is also a broad area what we call as a diffuse optical tomography. So today's talk, I will be restricting mostly to optical coherence tomography. This is the spectrum when it comes to how do we image, what resolutions we get, what is the depth of penetration that we do when we come to optical imaging. So if you look at the optical modalities, so those city fall somewhere where we get a depth of about a millimeter into the tissue. And so we get resolutions as high as about a micron to 2 microns to 10 or 15 microns. So compared to the standard imaging modalities like CT or MR, which is whole body imaging, these resolutions of light imaging, light-based imaging are very, very high. But the major drawback or the difficulty is that you penetrate only a millimeter. So you might be surprised. Why do you want to look at a technology which can image only a millimeter down the skin or down the tissue? So we will look at a couple of applications. We will look at what is the relevance of this millimeter when it comes to imaging. When it comes to optical coherence tomography, there's a broad class of applications which are already in clinic or clinical practice, and there are a bunch of applications which are at the research level where people are trying to explore applications of OCT in clinic. So the most common OCT application is something where you look at your eye or the back side of your eye, the retina, and we look at different layers of retina and see what are the anomalies possible. So you look at the macular region. So you can find out what are the thickness of various layers of the retina, and these thickness are very important because there are a lot of disease state pathologies where the thickness is affected, and you can use this for diagnosis of or screening of early stage complications like diabetic retinopathy or similar problems. So we can look at OCT and image the backside of the volume of the eye, and our image crossing techniques like segmentations can in fact segment out the volumes of layers of different layers of the retina, and these thicknesses can be used for quantification of various types of diseases or degenerative diseases in the eye. And this is probably the first type of OCT to get into clinical practice. And as you know, eye is the most simple and transparent, easy to access organ in our body. You can easily shine in light into the eye and look at the backside of the eye. So, but this is probably the simplest, and the farthest what OCT can do is put an OCT at the tip of a catheter, which is going into your bloodstream, into your arteries. You put a catheter into the artery, and you can image the walls of the artery. So below you see the ultrasound based intravenous catheter, and you can see an OCT based catheter. So the amount of information that this 1 millimeter of OCT can provide is huge. Compared to what you can see with an ultrasound based image. So you can see the high resolution image of the walls of the arteries, and it can give you conditions like plaque formation, the type of plaques, are there stenosis conditions, and if you're stenting the artery, you can look at the condition of the stent, the quality of the stenting, monitoring of the quality of the stent. A lot of applications can be done by imaging this 600 micron of the arterial wall, inner wall of the artery. So, and this is what makes a difference when it comes to OCT compared to what you see in an ultrasound or a regular imaging modality. So, and apart from this, there are a number of projects or research projects where people are trying to look at, say, demarcation of surgical demarcation of tissues in the case of cancers, looking at the quality of lymph nodes, so looking for staging of lymph nodes in the case of, say, for example, in the case of breast cancer, looking at the sentinel lymph nodes in the armpits. So OCT is one technology where you can really do an imaging of the lymph node without having to take them out. So these are projects where OCT has not yet reached the market, but there are clinical trials or phase 2 trials where people are looking at the lymph node, the whole capsule of the lymph node with an OCT, and trying to find out if are there possible metastasis in the lymph node, are these lymph node reactive or metastatic in nature. So these type of classifications can be easily made by imaging the lymph node with OCT images. So you can see. So this is actually one of the rat's lymph node which we image, and you can see the follicles and the regions where the reactiveness are the germination centers are very clearly seen inside the lymph node. So there are good classification of how lymph nodes can be staged with the help of OCT images. That's sort of the potential. And as you can see, you can really image the tissue in volume with high resolution. If you look at what is a basic principle of OCT, it is again like the same double slit interferometer that you studied in your high school classes, a Young's double slit interferometer, where the light from the two slits interfere, creating brightness and darkness, or constructive and destructive interference at the screen. So that's the same principle on which OCT also works. We shine in light into the tissues and collect the echoes of light. And these echoes of light from different layers of the tissue are interfered to create constructive interference. And from the constructive interference, we reconstruct back the tissue properties. So in a way, you can see that this is quite analogous to ultrasound. You shoot in sound and get the echoes of the sound back and reconstruct the image. Whereas in OCT, you shoot in light and get the pulses of packets of light which are interfering. Only thing is that we interfere the reflected or the scattered light back to detect them interferometrically, and that is how an OCT works. So if you look at this basic diagram here, this is like a traditional microscope or a Maxent interferometer. So you have a light source and two arms. One is the reference arm, other is sample arm. The light from the sample arm is coming to the detector, and the light from the reference arm is also coming to the detector. Reference arm is something where we have control on, and the light from the sample is the unknown beam. And you interfere these two light beams, and the interference is getting detected onto the detector array or the detector. So what is more important is that we talked about Young's double slit and the coherence. Here, actually, though we say that it is optical coherence tomography, it is actually a very low coherence of the light. The low coherence of the light is exploited to interference, because the depth of imaging, or the separation of the light that is scattered from each layer of your tissue, is decided by the low coherence property. So the low coherence property makes sure that light scattering from the top layer is not interfering with light coming from the next bottom layer. So there is a path difference between these two beams coming out, and that is where low coherence interferometry comes to play. Right. So and this how do we measure volume in the case of OCT? So we can shine in light and get the scattering and interfere them. So any one single point, if you image what we typically call as an A-scan image, and if we move the single point across the tissue, we call it as a B-mode image. It's very common nomenclature as we do in ultrasound as well. And by shifting with an X and Y galvo scanners, you can always have volumes of information. So you can have a single spot of light beam hitting the tissue, and you get one depth information, which is the A-scan. And by moving the beam in the X direction, you can have a B-mode image, which is nothing but a collection of A-scans. And then by shifting the beam in the Y direction, which is in the forward direction, you can have a volume image. So we can have volumetric imaging by moving the beam and creating X, Y, and Z depth information. So that is how we get OCT images back. I think we saw this basic principle, but I'm skipping this. And so when it comes to practical applications, there are a bunch of clinical platforms where OCT is being tested, starting from the tip of a biopsy needle, where you are using a small optical fiber at the tip of a needle, so that the light scattered from the tissue is being detected interferometry, and your needle can be guided to a particular tumor or a suspicious region into the tissue by looking at the scatterings from the fiber, those scatterings that are collected through the fiber. And OCT can be also introduced as a fiber probe at the tip of an endoscope, which would go into your GI tract for an upper esophageal endoscopy or similar applications. So in addition to this, there are also cases where OCT is used as a surgical microscope. So we can use on the surgical site to find out if you're looking at the margins carefully and seeing if there are tissues still left out in the body, which have to be removed. So OCT can be used for tumor demarcations. So these are number of applications where OCT finds applications in clinical imaging. So I would just show you one of the basic systems. This is a spectral domain OCT. When we talked about a spectral domain OCT, we talked about the basic interferometer. Here, how do we get information from each depth of the sample by moving the reference mirror. So by moving the reference mirror, we make sure that at every depth of the sample is being scanned, and interference from every depth is collected by moving the reference mirror. But if you use a source which is broad enough, with a broad band of light, you can actually get the whole information and whole information together as a packet of spectral interference. In such cases, you need to use, instead of a detector, you need to use a spectrometer, and the entire spectral interference will be spread into a linear detector array. So now you get the entire shot of depth information without having to scan the mirror. So we can keep the reference mirror stationary, and we can have a broad band beam passing through the fiber. And once the interference happen in spectral domain, so we can use a spectrometer to diffract the components of the spectrum into individual pixels on a linear CCD camera array. And this is how a spectral domain system works. And this is advantage is that you don't have any moving parts in the system, and you can have a fixed mirror, and you get the entire spectral interference on a linear CCD camera, which is much easier to process. This is a typical OCT system that we developed at IIT Hyderabad. This is a benchtop system where we decided we couple two superluminescent diode sources to get a light of bandwidth about 90 nanometers, center at 845 nanometer. And this was a fiber interferometer which we built, and it has like the 4 beams, one for sample and one for reference, and the other one where you connect to the spectrometer. And we built an in-house spectrometer. We built an in-house spectrometer where we could really look at the spectrum. So this is a linear CCD array, which can give a very high resolution. And so this is how the imaging system is. I have slowed down the system so that we can move the X and Y scanners and see how the spot is scanning onto the sample. So you can really see the scanning speeds at low speeds. So this is how you scan, and by moving the X and Y scanners, you can scan in volume. So so this is sort of like a good specs for the system. So this is a very high resolution system with about we have an axial resolution of about 3 micrometer and a spatial resolution of about 2 to 5 microns in the X and Y direction. So we achieved this spectral resolution with a very high resolution spectrometer with about 2048 pixels, and we are getting very high resolution in the spatial dimension, in the depth resolution of about 3 micron in the Z direction. So this is sort of like the interface where we can scan the samples. We will see the spectrum of interference, and we can reconstruct them into the window. So I will show you a couple of applications where we looked at the OCT in hospitals for looking at. We'll start with the most simple cases. Actually, this is a set of results from a commercial system from Zeiss. So this is looking at the eye, and so this is the macular region which you saw in the beginning, and I can really look at this volume of information and do some minimum algorithms and segment out the layers of the retina. And in fact, we can do the segmentation in 3 dimensions to get each layer separately, so that you can really look at each layer in the retina, find their thickness, and sort of use this as a quantitative parameter for diagnosis of diseases. So this is sort of what I showed in the beginning. And the second application with our system, we try to look at look at the GI tract. So we try to image the esophagus, or we try to image the tissue which is removed from the tissue that were removed from using surgery from the patients. The primary aim, what we looked at, was to find out if we are able to diagnose normal tissue versus malignant or cancerous tissue. So, and this was done ex vivo. That means that the patients who are enrolled for the study were diagnosed with cancer, and the tissue, the lump or the tumor in the stomach has been removed from the patient, and ex vivo image using OCT. The primary aim was to find out if OCT can diagnose, and second aspect of it is we wanted to also look at if we can see the margins of the tissue. So typically what happens is that, this is, if you look at the esophageal tissue or the stomach tissue has a very nice structural morphology. So the picture on the left show you a real nice morphology of the 1 millimeter of the endothelial inner lining of the stomach. So this has a lot of nice crypt-like structures, which are very well visible in any imaging. And as we see that there is a malignancy or a tumor which progresses, the structural morphology totally gets evaded, and you would see highly scattering tissue with actively dividing cells in this region. Which is going to be clearing the structural morphology. So this is what you see in a histopathology if you do a histopathology of the stomach from a malignant tissue. So what we really try to look at is, can we guide to find out if we can have margins of tumor versus normal tissue. And this was one of the studies we did with breast cancer. But so to find out, this is highly scattering adipose tissue in the breast. So you can, when it comes to breast, the differentiation between the tumor and the surrounding tissue is much easier, because breast in normal breast tissue you have a lot of adipose, which is low scattering and very, very clear in OCT images, and the tumor cells or the metastatic cells are very highly scattering and will appear something like this in the OCT images. So we did the same exercises with the GI tissues. These tissues were collected onto the eyes and imaged using OCT, and then later they were fixed and sent for histopathology. So you can see these are also all OCT images. The first one, you can see a normal tissue. As I mentioned before, you can see the nice structural morphology in the OCT image, which we saw in the histology also. And as the tumor progresses, there are beautiful things that are happening, which makes the tissue. First thing is that the tissue morphology disappears. Then the tissue becomes highly scattering. So the scattering nature of the tissue increases. And the third thing is that, once there are actively dividing tumor cells, there will be a lot of neovascularization or new blood cell formation into this region. So all of these small circular spots represents new blood vessels that are formed into this region, which are supplying to the actively dividing cancer cells. So neovascularizations or angiogenesis and highly scattering cells, which indicative of fast dividing cells with a high nuclear content, are salient features of any malignant cancer tissue. So, and as we see that, when you can see from image 1 to 3, there are clear differences. So the first one showing tumor, first one is a normal tissue, the second one showing tumor infiltrations, and the third one, which is a highly scattering or a fully tumorous tissue without any structure present there. So these are all undifferentiated and highly scattering cells present. So we did the studies on almost like 11 patients. So the trials are still going on, but we keep imaging the cells, and you can see if you look at this particular set, so the first one is quite normal. So we tried this is on a tissue which is post surgery removed from the patient. So you can see that as we move from one end to the other end, which is the normal tissue, we can see that the tissue morphology is disrupted slowly, and as we go to the tumorous region, it becomes highly scattering, which is shown in the 5 and 6. So the reason for doing this exercise is to find out, can we really distinguish the margin where the surgeon should operate? Or if the surgeon is removing the tissue from the tumor from the patient, how confident he can be to find out if he is clear, or his margins are very clear and that cancerous tissue or the tumor tissue is fully removed from the body. So this was one exercise that we did, and we have a lot of data to show that OCT can clearly differentiate the margins and the structural morphology of normal tissue versus cancer cells. So these are a bunch of other examples. I'm skipping all these images. So this is yet another margin. You can see, like, on the left side, you can clearly see the normal tissues, and as it goes, it becomes highly tumorous in nature. So this is a margin again showing normal versus malignant tissues, which are at a margin. So to summarize this study, like, we saw that, we can clearly see, I believe you can see the video. So you can clearly see the normal structures in OCT when compared to the highly scattering tissues, which are the tumorous in nature. We can see signatures of tumor with highly cancerous tissues, with a lot of blood vessels which are penetrating into this region. So all of these significantly tell that the tissue is cancerous or abnormal in nature. So I will brief a little bit about the second application we looked at, which is looking at the sentinel lymph nodes. And this is actually a typical exercise done in regular breast cancer diagnosis. So once there is a palpable lump or a tumor present in the breast, and while a mastectomy or a lumpectomy is being performed, so the skin is resected and the tumor along with the lymph nodes are exposed. These lymph nodes are the sentinel lymph nodes which directly drain from the tumor tissue. So typically, when the lump is removed or the breast is removed totally, so the surgeon actually takes out a lot of these lymph nodes from the armpit or the sentinel lymph nodes from the patient. And these lymph nodes are used for staging the cancer. Typically, the number of lymph nodes indicate what stage the cancer is, number of lymph nodes that are positive. So the difficult part is that once the lymph nodes are removed, the patient ends up in something called a lymphedema or swelling of the arms, because the lymph from the arms draining is affected, and you will see the fluid build up in that side of the arms in the body. So it's a condition that cannot be avoided, but if you can really look at these lymph nodes in situ without having to remove them from the body, you can really find out what is the quality of the lymph node, what is the status of the lymph node, are they positive, are they reactive, or metastatic in nature, and then you can take the decision right away without having to remove them, going to histopathology and finding out the state for the staging process. So this study actually we did in a rat. So we had a controlled set of rats where we induced cancer in the memory model. So we induced cancer in the rats, and then the popliteal lymph nodes from the rats were imaged using OCT. So you can see that there are very clear signatures of cancerous region present in the OCT. So what we did was that we had a control study from day 1 to day 9 from the rats which are positive, which are positively having a breast tumor, and so you can see clear differences in the capsule of the lymph node. And also you can see that as the tissue progresses, these subcapsular spaces get filled with a lot of tumor cells, macrophages, which creates inflammation in them. And end of the like when you look at the 9th day, the entire tumor is highly scattering, which is clearly indicative of a fully developed cancer or a fully metastatic node. So I haven't put all the different images here, but just to show that OCT can do imaging of the lymph nodes, I've put a couple of images only here. I will go to the next application where we looked at the oral tissue. So the oral lining or the lining of your buccal cavity is fairly similar to our esophageal or the stomach lining. So you can see that, this again, there is a clear structural morphology of the buccal cavity, and you can see differences in the lining of the oral cavity if there is a cancerous tissue. So again, like the tissues were collected from a dental medical college where there was suspicious lesions present or suspicious discolorations, which forced the clinician to suggest a biopsy. So these biopsy tissues were imaged with OCT, and we looked at the margins. We looked at the OCT of the image to find out whether we can see any signatures of cancer. So we could really see, in all the cases, actually, we in all the cases where the cancers were fairly visible and diagnosed right away by the clinician. So we could see that all of these cases we had very clear. These are the clinical and the histopathology reports compared, and we could very clearly see that the OCT showed clear differences in scattering signals in all these cancers. So this is an example of a verrucous carcinoma in the tongue. So this is an example where you can really see that this is like a leukoplakic region. You can very clearly see the changes in scattering, but you still see the basal membrane that is very impact. Now this is one of those stages where you can really revert an oral cancer, so that if adequate lifestyle changes are taken, these conditions can be reverted back to normal. So we could really see that OCT can distinguish between a normal tissue and a cancerous or a precancerous lesion region. Right. So we also looked at the signatures from OCT to find out, can we see a little bit more details? So because in most of the oral cancer regions, there is also the presence of keratin in the tissue, which is also a very clear indicator that it could be a cancerous tissue. So these were all, like the green images shows the keratin staining in the tissue. We can clearly see that these keratin folds are highly scattering and creating scattering in the OCT tissue as well. So looking at the A-scan OCT scattering itself, you can really conclude that these high scattering regions clearly indicate the presence of high keratinous structures in the OCT images. So we have been working on an algorithm where you can really look at the scattering of the tissue and compare them to find out, based on the scattering itself, can we really classify the OCT images into normal tissue and cancerous or precancerous tissue. So we have tried a small learning algorithm, and first we started with phantoms with a different type of scattering particles and find out, can we use a training algorithm to find out if we can classify OCT scattering, classify this scattering from these OCT images, and find out if we can classify various tissues with different scattering properties. So we are quite successful, and we are still looking at biological tissues and find out if OCT scattering can be learned with a machine learning algorithm, and we can do an automatic diagnosis with the scattering data. So I think with this, I will wrap up the talk here. These are some of the challenges in translating OCT to the market. Like, we need to really look at good clinical data, and large volumes of data need to be generated to find out whether we can apply this to various diagnostic applications and screening. But OCT has a very high potential in clinical diagnosis, and we have also been trying to bring intelligence to OCT data by looking at developing learning algorithms to find out and quantify the scattering properties of tissues, and look at how we can segment the data and can we use this information for demarcation of surgical margins. So, and finally, the most important part, like, there's a huge market in the country where people are looking at point of care and portable systems for OCT applications, where you could really look at a handheld system for oral screening applications, like oral screening or screening for cervical cancer and similar things. So there is also a need for development of new light sources for these portable and fast OCT systems. So I think with this, I will wind up my talk, and the floor is open for questions. Thank you very much once again. And if you have questions, feel free to ask.
Thank you, sir. Are
Thank
there
you.
any questions to Dr. Renu John from the participants?
So this is Kavita. How are you?
Hi. Good evening, ma'am. How are you?
So I wanted to listen to you, and I mean, I don't have to tell how interesting it was, because it really was very interesting. I could see the wide variety of applications you were talking about. It's very surprising, because as far as we've been hearing OCT is into the retinal business, and to an extent into the other imaging. But what was surprising was the surgical margins that you were talking about. So you must be dealing with a lot of surgeons and other clinicians also, right, sir?
Yeah, so most of these studies...
it's a political question. Is it not difficult to convince them about the findings, or are they looking forward for...
so that's a good question. But, it has been difficult earlier. But, over the period of time now, it is quite exciting for them to look at the other side of the table and find out, but what you're seeing, are you seeing something? They are very excited about what we are seeing. So there is a real change from the clinical side to look at newer technologies, how it can be used. And the clinicians are really interested in looking at what is evolving at the academic side as well. I would say, I have received a lot of positive responses and very excited physicians, clinicians, and surgeons in research now.
Must have been very challenging to convince them initially, because they have this divide. But once they find out like how supportive the findings are, I think surgeons are more welcome to such specifications, because they cannot have any kind of risk in defining their margins. So if something is quantitatively given to them, I think they'll be looking forward to it.
So
you must be using a lot of quantitative parameters as well, right, sir?
Yeah, we are looking at
a lot of quantitative parameters.
we are really trying to quantitatively conclude on the scattering and all. So there are a bunch of parameters which are still on the borderline, whether we say that for sure this is yes or no. That is where I showed those keratin scattering and all. So these are yet not conclusive, but we see that there is a high potential in quantifying those numbers, because finally, end of the day, clinicians they want to say that it is yes or no. If OCT can do that. So there are also see some of these problems are too trivial when it comes to a surgeon, because for a stomach or a GI surgery, they don't care if they go a few centimeters to move the tumor out. But when it comes to a neurosurgery case,
exactly,
it's very critical for him to look at another 10 or 15 microns, which might be overlapping with a more sensitive region of the brain. So if he has a tool in his hand which can give him exact margin, there is nothing like that. So we are still at the starting stage. It's 10 years we have been working on this problem. It is not like one day. So we have gone through a very long journey.
The kind of You see that, and also the indigenous spectrophotometer that you were talking about. So how is it like? Is it into clinical practice now, or I saw something developed in-house.
Yeah. So
showing.
what you saw, the entire OCT we have built. I think you have one of the OCT experts with you right now. Right,
Yeah.
You have, yeah. So you can build it. I mean, it's not very difficult. If you have some basic optics, you can really make neuron spectrometers. And you cannot really bank on commercial spectrometers on your custom-made instruments. So when you are making your instruments to get the best results, you have to make your own spectrometers also. That is also very critical.
I'm sure she'll make the best use of it. She's come into the department now only.
Yeah.
I actually didn't know that she knew you already. It was a surprise for me, So now
Yes.
that you are also into it, I think there'll be very good research happening. And Dr. Paulin, I'm waiting to see something interesting like this.
Yes, ma'am. I'm looking
in
forward for
assistance.
more collaborations with Professor Renu.
Hey.
He's always there to support us, right, sir?
Yeah, always. I think it's all science,
Yeah.
nothing else.
Thank you so much for the nice talk, interesting conversations, and the kind of support that you've been showing also, sir. Thank you so much.
Thanks, and all the best to you. Thank you. Bye-bye.
Bye.
Thank you, Professor Renu. Thank you so much.
Are there any more questions from the participant side? If so, you can use the chat box or unmute yourself to do so.
Right. So feel free to write to me. So I will leave my email at the chat box. Right. Thank you.
Okay.
If no other questions, then thanks everybody. Bye.
Thank you so much, sir, for graciously complying to a request despite the changes in the schedule.
Absolutely.
And for also patiently bearing with us through the same. Thank you for giving us an overview of on the high resolution imaging technique, OCT, for the diagnosis of early stages of pathological conditions, including the cancer. We are sure that research scholars and audience interested in exploring and carrying out research in the field of biomedical optics would have been very much benefited by the detailed explanation that you have provided for us. Thank you so much, sir.
All right. Thank you. Bye.
We now come to the end of day 2 of the 8th International Conference on Biosignals, Images, and Instrumentation for the year 2022. We thank all the attendees for their valuable time and contribution throughout the day. I hope day 2 of ICBSII 2022 was informative and thought-provoking for all the young attendees and the participants. We will meet tomorrow again using the same link for the first keynote session of the final day at 8:30 a.m. Thank you so much.